such as Dr. Ham at the Medical College of Virginia in Richmond in the US, who argued that we shouldn't be doing this experiment. We should use a larger image on the rabbit retina or the primate retina or the human retina in determining what would be the threshold from a tiny, tiny lesion and simply extrapolate by basic physical principles. We know, for example, what is the limiting spot size on the retina. It's a little diffraction pattern of something on the order of 5 to 15 micrometers. And we also know from a lot of research how this is never quite achieved because we don't have the very best optical system in our eye, but we are able to see sharply, largely due to the fact that we have a very good image processing system in the visual cortex and the retina in the brain to permit us to see fine details such as two stars separated by a minute of arc, which we otherwise should not be able to see. One of the ways we have for determining how how good an image really is on the retina is by knowing and measuring the modulation transfer function. This is an optical physics technique that's used to analyze the quality of a camera lens or a telescope, and it can be applied to the human eye as well. Basically what happens is we have a sharp contrast with a target, and then we have a blurred contrast at the image plane. And we can measure how that changes, and we can extrapolate to calculate exactly how small that spot is. You can actually visualize the interesting phenomena that's related to, it's not the MTF, but it's called the contrast transfer function. And for those of you who are sitting in the front of the auditorium and see this close up, you'll see a different spot, different area here where there still is detectable contrast compared to the people at the back of the room. And if you move back and forth, you can see how this changes. And this is all related to the fact that in the human retina, our image processing is sharpening up one particular frequency that's very important. Well, the implications of all this is that from a thermal injury standpoint, which is normally what we're dealing with surgical lasers if we have an accidental exposure, there's a very, very sharply defined probability of seeing an injury if we have a large image size. If we're doing studies on the cornea or on the skin, you just change the radiant exposure or the irradiance by a factor of 10%, and you go from always seeing a lesion to never seeing the lesion. And that would be this line here. But the statistical spread of visible lesions detected in the experiment where you look for a tiny lesion on the retina looks more like this. And what happens is that as you perform more and more exposures, this steepens up. And so what really was happening is we were using this value as somehow being the important value because it's statistically the most reliable in comparing data from laboratory to laboratory, but in fact it wasn't an accurate measure, and particularly as we did more and more exposures from a multiple exposure, it appeared like the threshold was getting less and less, when in fact we were just getting a more reliable measure of what the true threshold really was. There are variabilities. For example, if we look at the retina in a flat preparation like this and the pigment epithelium, we see a variation in pigment. For example, here's an area, if you had a tiny lesion here, there's more pigment to absorb and a higher temperature possible. But if we go over here and had an exposure here, there's far less pigment. So there is a variation of perhaps a factor of 2 that really happens biologically. But the biggest thing that happens is that with every pulsatile change in intraocular pressure due to blood flow, arterial blood flow, the actual focal image moves in and out ever so slightly over a few hundred micrometers, with the result that some will get to the worst case and some won't. So in any case, we're going to see a great reduction in the need for this repetitive pulse correction factor, and if you have a laser product with many pulses, it may be that the safety limit will go up in the future, which will reduce concern about the safety. The next point that I wanted to mention is that there was another artifact that came about in trying to simplify exposure limits some years ago, and we had a much, much larger safety factor for large image sizes. I won't try to translate all this stuff on this graph, but to simply say that the earlier or the current exposure limits have a movement like this, and there's been an effort to change the shape of this so it's more accurate with regard to tracking the biological data. This turns out to have a real benefit in the safety analysis of intense pulse light sources and large flash lamps and large laser arrays that are pulsed, because the exposure limit will be increased, reducing some concern. Another very interesting area that has some implications for safety, which we're currently not fully sure about, has to do with the discovery that in addition to the rods and cones that are down here in the photoreceptor layer of the retina, this is a cross-section of the retina, way up here, after several neural processing steps of the visual signal, we have ganglion cells, and some ganglion cells turned out to contain a photosensitive molecule, melanopsin, which is a bistable molecule that is light sensitive. It can be pushed in one isomerization by red light and another isomerization by blue light. The most interesting area is that when blue light, peaking around 460, 470 nanometers, is incident on the retina, which is most dominant in midday when the sun is high in the sky and light is quite bluish, it pushes the melanopsin into one position and also sends a signal back a different pathway than is applied in vision, and goes to neuroendocrine and other parts of the brain that influence circadian rhythms and other things, such as pupillary opening and other things. When the sun is low in the sky in the morning or late in the day, it is reddish, yellowish. It has little blue light present, and therefore it gives a different signal. So we have a sensor system that's providing circadian influence. What's the implication from a safety standpoint? As we move to more LEDs and blue light phototherapy and more LEDs for illumination, if our eyes are constantly exposed to very blue-rich light, we might just have some effects on our sleeplessness. We don't fully understand all the impact of this, but I can tell you I was evaluating a phototherapy array of blue LEDs a few years ago when they were very new, and I was making my measurements late in the evening. I could not sleep the whole night. I absolutely couldn't fall asleep. So be cautious if you're working with blue LEDs. Think about that. And of course, this is of importance in treatment of winter depression, which is a common issue in very northern climates like in Scandinavia, Alaska, and Canada, and so forth. These neuroendocrine effects also tell us that perhaps during retinal phototherapy, we should be concerned about damaging some of these sensors when a patient is being exposed to short wavelength photocoagulators. This has become a big issue in surgery for cataract, and there are companies, for example, that have intraocular lens implants that simulate an older lens that is slightly yellowish, and the impact is to try to reduce the potential hazard to the retina from bright light, but at the same time there are concerns that it might interfere with the melanopsin function. So much of what we know from setting standards for laser safe exposure for chronic exposure relate to how people are exposed to various artificial sources and the sun. And of course there's a wide range of exposures, from the lights that are comfortable to view, like ordinary frosted lamps and a candle flame or a frosted fluorescent lamp. These are all within our normal physiological exposure range for retinal exposure, about 10 to 50 microwatts per square centimeter. If we momentarily look at the sun, it's 1,000,000 times more intense, and there we can start to approach a thermal effect. But in between, the potential risk is all related to how much short wavelength blue and violet light we're exposed to. With lasers, it's rare that we have continuous exposure for any length of time. Certainly, accidental exposures to visible sources, we normally have the aversion response, and it's only in some applications where we're constantly working with lasers that we have exposures to the eye from scattered light and so forth that might come into question from a standpoint of delayed chronic effects. This is one of those types of light sources I mentioned that is quite nice at the middle of the day or perhaps even in the morning, but not in the evening. So our photobiological hazards depend not just on wavelength, but also upon exposure duration, source brightness or radiance, and the exposure geometry. The position of different sensors in the retina depend upon location and how we're exposed to sunlight. When we're in bright sunlight, our upper lid comes down and acts as a shade and protects the inferior retina. And this fits because when we look at an elderly patient's retina, we see more signs of aging in the superior retina than the inferior retina. When we look at conventional light sources, this is where we have the potential for very lengthy exposure day after day. Normally, laser exposures are not really existent for the eye during normal applications because we don't get directly into the beam. So we're dealing with accidental acute exposures to very, very high levels. And most of our safety procedures are all oriented toward trying to minimize that type of exposure. But with things like low-level laser therapy and phototherapy and the use of lamps, we have a greater chance of very lengthy exposure. And generally, the two most significant hazards from lamps from lengthy exposure are called the blue light photoretinitis hazard or the ultraviolet hazard, which is really to the cornea and to the skin. There are some sources that are high risk from both, such as a high-pressure arc lamp, some which are not at all a hazard, such as our conventional lamps that we use in interior lighting. There are safety labels that are being developed for lamps for protecting against ultraviolet radiation, and also labels that have been proposed for both lamps and lasers, but there's a lot of